My project was to find a solution to BBN abundance discrepancies using dark matter. Hi, I'm Sofiya Zuykova, and I've been the mentee of my mentor, Anna Catherine Burns, who has worked alongside this project with me for about 10 months now. And the reason why I chose this project is because I'm both very passionate and curious about the subject as I plan to go into this field for university. So I wanted to contribute to my own community through this project. And I'm currently recording from Canada, Alberta. So some context for this project is that in 2021, the Empress collaboration reported observed values of helium-4 that deviated from standard BBN predictions. Since then, numerous theoretical models have been proposed to explain the discrepancy between observed and predicted abundances. The goal of our project was to alleviate this tension between experimental and BBN abundances of helium-4 and deuterium using a dark matter model coupled to neutrinos with a varying mass and delta ineffective. But first, some background information since I'm sure that didn't make a lot of sense. Big Bang nucleosynthesis, or BBN, is a theory that explains the production of light nuclei, including but not limited to helium-4, deuterium, and lithium formed shortly after the Big Bang. Theoretical predictions from BBN align well with the observed abundances of these elements in the universe today. Because of this, BBN is considered a reliable model for understanding the conditions of the early universe, specifically when concerning elements such as helium-4 and deuterium. Additionally, if there is a discrepancy between the observed values of elements and the predicted values, new physics can be explored to potentially alleviate this tension. Before BBN, neutrinos played a crucial role in shaping the early universe. Neutrinos are the lightest known massive subatomic particles, meaning with mass, and they interact with other particles, specifically charged leptons and quarks, through the weak force. Neutrinos participated in the conversions between neutrons and protons. These conversion rates freeze out as the universe expands and loses energy density, meaning prior to BBN, a fixed number of protons to neutrons existed in the plasma. This affected how much of each light element could be created during BBN. Helium-4 is especially sensitive to this ratio between neutrons and to protons, as the majority of neutrons end up forming into helium-4. To put this into a larger timeline, here we have the inflation, which is the initial expansion caused by the Big Bang. And as we see our first particles being created, this is when we have our neutrino exchange rates occurring, converting neutrons to protons back and forth. And as the universe continues to expand, there's not enough energy to continue these conversion rates. So they freeze, and that's finally when BBN occurs. And we see our elements being created. So another important factor at the time of BBN is the energy density of the universe contained in relativistic species parameterized by N effective. And the reason N effective is so important is because it impacts the expansion rate of the universe and in turn the abundances of light nuclei. This is because the slower the universe expands, the more time elements have to form, which can result in more heavier elements forming and less light elements forming. And this equation above describes the total radiation density expressed as a function of N effective, which accounts for any extra relativistic degrees of freedom beyond the standard model, which can then be further simplified into the equation below as a ratio of energy density of neutrinos to photons. Now, what is delta ineffective? Delta ineffective is a deviation from the standard number of neutrinos, and it is used to describe radiation density at the time of BBN. Finally, what is dark matter? Dark matter is an umbrella term for non-visible matter that interacts through gravitation with visible matter. And considering that about 85% of the matter in the universe is dark matter, it plays a distinct role in shaping the dynamics of the visible universe. This study focuses on altering the mass of dark matter coupled to neutrinos from 2 to 10 MeV, as well as changing delta ineffective, the amount of added radiation density as compared to the standard value. Since our model is coupled or interacting with neutrinos, This species of dark matter would directly impact the proton and neutrino conversion rates neutrinos play a role in. And after these conversion rates freeze out with the expansion of the universe, the ratio of protons to the neutrons left for synthesis would be impacted. So in order for us to find the most plausible parameters of dark matter mass and also ineffective in this model, the predicted abundances of helium-4 and deuterium must match the observed amount today. Our model was only tested using deuterium and helium-4 because these light elements have the smallest margins of error, so we would be able to verify our results more clearly than if we used other elements. Now that we understand the theory, how do we actually go about testing this model? To conduct the study, we used a publicly available Python code Primordial to investigate the effect on the final abundances of helium-4 and deuterium. Primordial is an open source program that simulates the first 20 minutes after the Big Bang and calculates the abundances of light elements as well as the amount of radiation present at the time of BBN using an effective. Primordial is broken down into modules, each module serving a separate function and simulating Big Bang conditions, as shown in the diagram below. We started by programming dark matter with a varying mass of 2 to 10 MeV into Primordial and varying delta ineffective systematically between -1 and 1 to model a range of light nuclei production scenarios. The dark matter mass range was chosen based on prior theoretical models suggesting this mass scale could influence thermal processes during BBN. And the delta ineffective range of -1 to 1 was chosen because it captures both substandard and excessive radiation energy densities that could plausibly arise from additional relativistic degrees of freedom or non-standard decoupling effects. After this, we recorded the results and compared them to the experimental values of helium-4 and deuterium abundances to deduce a range of parameters that would alleviate the tension between experimental and theory values. Our study found that changing dark matter mass had little effect on the abundances of helium-4 and deuterium using primordial. However, changing delta ineffective impacted abundances, particularly deuterium, strongly as indicated by the range of vertical color gradients in comparison to the horizontal color gradients. The standard value about 0.248 for helium-4 and about 2.527 for deuterium falls within the gray region on both figures. The red represents high abundance values of the respective light element, and in contrast, blue regions indicate lower abundances of the respective light element. The black lines on both figure 1 and 2 represent the PDG observed abundance values plus or minus 1 sigma, respectively, which were the standard observed values for both elements until Empress released new data for helium-4. The red dashed lines represent the Empress values for helium-4 plus or minus 1 sigma, respectively. The tested model alleviates tension between the newest experimental values from Empress of the helium-4 abundances and the standard theory value. The addition of dark matter with a mass between 2 to 10 MeV paired with a negative value of delta ineffective in the range of -1 to -0.5 produces helium-4 values in agreement with Empress. As for deuterium, a wide range of both parameters, 2 to 10 MeV for dark matter mass and delta ineffective from -0.45 to 0.2, can alleviate the tension depending on the combination of parameters. But ultimately, a higher dark matter mass requires a higher delta ineffective to match the PDG values for deuterium. A potential explanation for these results could be that a negative delta ineffective corresponds to a lower energy density, which would in turn slow the expansion of the universe. This slower expansion provides more time for light nuclei to undergo fusion into heavier nuclei, thus lowering the final abundances of helium-4 and deuterium. Lighter dark matter has higher kinetic energy than heavier dark matter. This means that when light dark matter decays into neutrinos due to its coupling, the resulting neutrinos carry more energy. As a result, energy density is increased since relativistic neutrinos contribute to a significant portion of the radiation content of the early universe. This elevated energy density leads to a higher expansion rate. A higher expansion rate would give less time for heavier nuclei to form, resulting in a greater abundance of lighter nuclei. And in the case for deuterium, this rationale could potentially explain why a lighter dark matter mass resulted in a higher abundance. Thank you for listening to my presentation and for having me speak at the symposium. Here are all the references that went behind this project and the research. And here in the appendix, we have the code we use to program dark matter into Primordial. Thank you.